one more case to consider before we move on to the non-bonded terms in molecular mechanics force fields is out-of-plane terms. So these are sometimes called out-of-plane or improper torsion terms, and they look very similar to torsions and they work very similar to torsions, but they're designed to handle a very specific case of torsion angle. So this would be an out-of-plane term, sometimes would be lumped in with the torsion terms, so as they're calling it, an improper torsion. So this would be a sum over all the out-of-plane angles that you've got of 1/2 of a parameter v, same thing as from the torsion terms, times 1 plus cosine 2 phi, the out-of-plane angle, minus 180 degrees. So you'll notice here that the sum from 1 to 6 is gone for n is only 2 in this case, and we don't have gamma. Gamma is always 180 degrees for the offset. Okay, so what's going on here? So we have our parameters, and in this case that is just v, which is just the rotation barrier or the out-of-plane barrier, which is going to have the same units of whatever your energy has, typically kilocalories per mole, maybe something else, maybe kilojoules per mole, maybe Hartrees, but most commonly you'll see kilocalories per mole. Okay, and then the variable of interest is going to be phi, which is our out-of-plane or improper torsion angle. And once again, we have the caveat of angles. We need to pay attention whether it's in degrees or whether it is in radians, more commonly in degrees, but again, don't assume that it is until you check. Okay, so if we have something like formaldehyde, what we want is we want formaldehyde to be planar, but there's no term here which is going to restrict it to necessarily be planar, because we're going to have a CO bond term, we're going to have two CH bond terms, we're going to have OCH bond angles, 2 of those. We're going to have an HCH bond angle. But none of those actually restrict the molecule to be planar. And then we could try to do that with a torsion angle, but there aren't actually any torsion angles in the molecule. You need 3 consecutive covalent bonds to form that, and we only have 2 at the most. But what we do have is 1 atom with 3 covalent bonds. So what we can do there is we can either define the out-of-plane angle or we can define an improper torsion angle, whereby we define something like 1, 2, 3, 4, where we actually include a torsion for where the last bond isn't actually 2 atoms that are bonded, but they're representing this out-of-plane angle here, where if we have the 2 H's, the carbon, and the oxygen. So if we plot this potential of what this is going to be, it starts at 0 degrees. Out-of-plane angle of 0 degrees means you're in the plane. And then the range of that is from minus 90 to plus 90. It's signed, so negatives are below, positives are above here, depending on which order you specify the 2 hydrogens. So that can go from a range from basically 0 up to 90 degrees there. So that would start at 0, and if we do first the absolute value of phi, it's symmetric with respect to 0 here. So start at 0, go up, and then reach a maximum at V at our rotation barrier in kilocalories per mole there. So we've got an incentive here in this term, in this out-of-plane or improper torsion term, to keep our formaldehyde planar. We could do the same thing in a molecule like benzene. Benzene, it's a little different because we could have done it through torsion angles, but we could also do it through these types of angles as well. So we'd have 6 out-of-plane angles there in benzene, keeping everything around each carbon atom in a plane. We'd have 1 here in formaldehyde if that was the case of what we were doing there. So these are typically on the same order of magnitude of the things that we're looking at for torsions. So the V for XX, 2 general atoms, CaHa, which are the aromatic carbon and aromatic hydrogen in amber. So if we had, carbon, 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 hydrogen for this particular out of plane angle, then that would equal 1.1 kilocalories per mole. So there's a 1 kilocalorie barrier to these hydrogens going out of plane there and going around this benzene. Okay, so how does that work in practice when you actually look at a specific molecule? So we've got our formaldehyde here. So we need to keep each CH and CO bond length the same. We need to keep the two OCH and the HCH bond angles the same, but we're just going to vary the out of plane angle there. So that trajectory looks something like this, or keeping those bond lengths and bond angles the same, but you can see it's going in and out of plane there. The hydrogens are moving more than the oxygen because the oxygen has a much heavier mass, but you could equally imagine it as the hydrogens being fixed and the oxygen wagging in and out of plane there. So that's the particular motion that we're trying to make sure that it doesn't have absolutely free motion. It can move a little bit, but overall the equilibrium structure is the planar case, and the molecule has an incentive to stay in the plane. So those are the out of plane or improper torsion angles, which aren't always necessarily mentioned in the energy function, but you need to keep in mind because they might be in there, just not in the officially documented equation.